What does constant mean?
It is a real number.
It is that number at every point.
What does the word constant mean? Put the paper away. What? So therefore, what is? So it's also it doesn't what? Doesn't change. So derivative is a measure of what?
Change.
The rate of change. So if it's not changing, what's the rate of change?
0.
Got it. The derivative of x.
1.
Yeah. Coefficient is 1. Derivative of x squared we've seen is 2x. Derivative of x cubed is 3x squared. What's the derivative of x to the fourth? So what we get to play with here is this equation right here. So let's start with f of x is c times x to the n power. That's what we get to generalize. What does that represent? Can we factor this?
Yes.
What do you think? Everything is factorable, so I'll ask one more time.
Yes.
Can you factor this?
Yes.
Yes, you can. Everything is factorable, therefore you can factor this. Does it mean that it's always easy to factor something like this?
No.
No, it's not. It's not. It's not. Factored out of C. And then we're left with this. This is kind of where, this is exactly where we're stuck up here. We're here and we're right here. What's the issue we have? We need to factor this. Exactly. We do need to factor this. Now, I'll just tell you right now, I'm not going to have you do, you're not going to need to really know how to do that right there, but something that's very similar. I mean, this is very similar. Do we have the same power here and here?
Yeah.
We have the same power, so we have something to a power minus
Something.
else to a power. So could we use this formula right here?
Yeah.
We absolutely could. In this case, x is x plus h, and a is
X.
x. If we make that direct substitution, which is fine, it doesn't change anything, we end up with this. What cancels now? No.
X plus X minus A.
The x minus a's cancel, and you're left with c, the limit as x goes to a, of x to the n minus 1 plus x to the n minus 2a plus x to the a n minus 2 plus a n to the n minus 1. Now we're plugging in x for what? A. So we end up with c times x to the n plus x to the what power? Well, x to the n minus 2 times x, right? Plus x times... It will be. I haven't simplified it yet. X times x to the n minus 2 plus x to the n minus 1. What do those all become? It's x to the n plus what? What does this become? X to the n minus 1. What does this, what is, oh, this is a minus 1.
Yeah.
Minus 1, yeah. And what does this one become right here?
X to the n minus 1.
And what's this, oh, the last one already is x to the n minus 1. The real question is, how many x to the n minus 1s do we have? Nope, we do not have infinite of them. How many of them do we have? We have n of them. We do have n of them. That is correct. We do have n of them. You can figure that out. You're counting down right here, x to the n minus 1, x to the n minus 2, and then what's the power of x right here?
1.
And what's the power of x right here? X to the 0, right? So you're going from n minus 1 all the way down to 0. If you go from n minus 1 all the way down to 0, how many things have you counted? N of them. If you go from n to 1, you've counted n things. If you go from n minus 1 to 0, you've counted n things. So how many of these do we have right here? N of them. So if you have n of them, you can write it as c times n times to the n minus 1, absolutely. Yes, so what have we proven? If, yeah, we've proven if f of x is equal to c x to the n, then f prime of x is equal to cn x to the... This proof right here only works for rational numbers. You have to do some more magic if you're talking about irrational numbers. You can extend this proof. Right now this essentially works with any whole number. You can extend this pretty easily to any rational number, any fraction. You have to add in a little bit more logic to do irrational numbers. We're not really quite going to get it. We don't really need to get into that, but this works for any power of n. In particular, though, what was the heading for this section? Polynomials and exponential functions. Which kind of function were we just dealing with here? Polynomial. So did we just come out with a fast way to take the derivative of any polynomial?
We did.
Yes, many of you have seen this before. It's kind of like the first thing you learn. You should theoretically think this is pretty cool. Is this the only thing you're going to learn as a tool? No, you're going to learn many different tools for differentiation. There are many things that this doesn't work for. So for example, if I gave you f of x is equal to 2x cubed minus x squared plus 7x minus 3. Jackie, what's the derivative?
6x squared minus 2x plus 7.
Yep, that is the derivative. Was that a little easier than using the limit definition? Yes, that was you can say that. That was, everything's relative, but that was a little easier than using the limit. Tell me what I should change it to. 3 times. Yeah, so therefore f prime of x is, and you could say that's negative 6 over x cubed, exactly. So we can use the rule we just learned, absolutely. So what about this one? What should we do first here? What is that equal to, Maddie? X to the what power? Close. 7 over 3. So therefore f prime of x is equal to, what do you think it equals, Hutch?
7/3 over 4.
7/3 x to the
4 over 3.
to the 4 over 3. Subtract 1 from the top. Yeah. Works with anything. Absolutely. Absolutely. Good. So you take each derivative separately. Nothing too earth-shattering there. If I just gave you this right now, and I'll tell you this right now, what's a really common wrong way to differentiate this? Some people, the wrong way, you see this all the time. Yeah, you see this. You see like x times a to the x minus 1. Is that even remotely correct?
No.
No, I'm showing you this now so you can go like
about 3 times?
you'll do it like 3 times. This is like saying a plus b to the x power is like a to the x plus b to the x, like taking the power and like bringing it inside. This is those things that like the humming sound starts in my ear and like gets bigger. So we're just showing you this right now. No. What is it? Boo-how. Boo-how, right? Is that correct? Okay. No. Okay. What would be a great thing if we wanted to solve? We can't plug in h as 0 into this. What would we like to do? We'd like to be able to cancel. At this point, are we able to cancel? No, we're not able to cancel. You can change it. Yeah, change it a little bit. Limit as h goes to 0 of a to the x times a to the h minus a to the x. You can do that, right? Limit the exponent.
Yes.
Right. Now, what can you factor out of the top then?
A to the x.
So now we have a to the x times the limit as h goes to 0 of a to the h minus what? All over? All over h. Yeah. This is kind of
2 to the x minus 1.
all over x. And what would you do?
And then you keep plugging in smaller and smaller numbers for h.
Or look at what?
The table.
Look at the table around 0. That might be just easier. And you'll get it. It looks like it's around point. Is it going to be defined at 0? No, but should it approach 0.69 from both sides?
Yeah.
Yeah. So if you do it for 3, you get 1.10. So what we get here is that the derivative of 2 to the x is around 0.69 times 2 to the x. The derivative of 3 to the x is around 1.10 times 3 to the x. Now this allows us to actually find it, but is this an exact answer?
No.
No. So are we satiated?
What does that mean?
What does satiated mean?
Satisfied.
Are we satisfied? No, we're not satisfied. We would like an exact answer to this mess. Okay. So 1 is our favorite coefficient in most cases. Sometimes it's 0, but 1 is our favorite coefficient. We like it to be 1. So we'd love the function where f prime of 0 is
1.
If that's the case, what's really cool about this is, what do we have right here? Our function tells us that if f of x equals a to the x and f prime of x is a to the x and f prime of 0, if f prime of 0 is 1, then f prime of x is equal to what? Equals f of x. Is that pretty cool? A
Yeah.
function is the derivative of
A function.
itself. A function, we've just shown that maybe there is a function whose derivative is itself. Is that pretty cool?
Yeah.
Would that be pretty neat to know? Yeah, it would be pretty neat to know. Okay, so what we're looking for is we need to find an a value such that the limit as h goes to 0 of a to the what power? A to the h minus 1 all over h is equal to? We want that to, sorry, not 0. We want that equal to 1. What does a equal? We would love to know what a equals in that case. So let's keep on going. Derivative is getting steeper as a gets bigger. So it's between 2 and 3, right? So how could we get closer to the actual number. Instead of 2 and 3, we pick
Five.
maybe 2.5 and see where it is, right? So could we get arbitrarily? So if we zero in on this number, what are you going to zero in on? What number?
E.
You will zero in on E. So what does this tell us? What does this mean? If E is squared. If f of x is equal to e to the x, then what?
Then f prime of x is equal to e to the x.
Yeah, is that pretty cool?
Yeah.
The y value of the e to the x function is the derivative of e to the x at that x value. Is this going to come up hundreds and hundreds of times in the course of the next year for you?
Yeah.
Yes. E to the x is going to be a very good friend of yours because when you take the derivative, it stays calm. Many functions, when you repeatedly take derivatives, tend to go like this. Like trig functions explode you, okay? Trig functions go berserk. E to the x, you're like, nice. Okay? You'll like this.
We're going to see that. We're definitely
That's there. ln2. Please leave it in ln2. Yes.
Logs are...
Is the square root of 2 a rational number? It's not, but do you know why?
No.
Yeah, I mean, there's a lot of digits, right? Finding it, do you analyze patterns? Do you try to find? No. So what we're going to do, we're going to assume it's rational. So if it's rational, what does that mean we can write it as? A fraction in lowest terms, right? We'll call it p over q. If it's in lowest terms, so it's in lowest terms, so can you reduce that any further? No, there's nothing to cancel, so it's like 5 over 7. Can you reduce 5 over 7? No. Okay, so I'm going to multiply both sides by q. I'm going to square both sides. Are we okay with this? Yeah. P is equal to 2q squared. What can you tell me about P? P and Q are
P squared on the bottom.
integers. Sorry, yes. P squared. So hold on. What can you tell me about P squared? What's one of the factors of P squared? Say it louder. 2. What's another factor of P squared? Q and Q squared, right? So 2, Q, and Q squared. So what can you tell me about P squared, the number? Is it odd or even?
It's even.
It's even. Do you agree with that?
Yeah.
It has to be because 2 is a factor. You okay with that? Okay. What's an odd times an odd?
Even.
Really? It's an odd. 2n plus 1 times 2n plus 1. That would be an odd times an odd. 2n is an odd number. If you multiply that out, what do you get? You get 4n squared plus 4n plus 1. This is even, and what does that plus 1 make it? Odd. So there's your proof. That's like just the note for proof. Okay, so an odd times an odd is an odd. What's an even times an even? It has to be an even. You really agree with that? Yeah. 2n times 2n is equal to 4n. So 4 is a factor, so it has to be even. So therefore, if p squared is even, therefore p has to be. If p squared is even, so therefore what does p have to be? Even. Are you okay with that so far?
Yeah.
So if p is even, what has to be a factor? 2. So therefore, p is equal to 2 times some number k. Are you okay with that? Let's substitute now. Let's take this right here and plug it in right there. So what do we now have? 2q squared is equal to
2k squared.
2k squared. So 2q squared is equal to 4k squared. Divide both sides by 2 and you get q squared is equal to 2k squared. So therefore q squared has to be even, right? So therefore q has to be even. Are you okay with that? So if q is even, q is equal to 2 times some number L. Where can we plug that in? 2L, we plug it in for Q. And what do we end up with? 2L. No, but that's exactly what we're not going to do, but that's exactly what we're trying to aim for. So we get that, right? So what do you end up with?
Sure.
What do you end up with?
4.
4L squared is equal to 2K squared. What did we cancel out here? So could we keep going here indefinitely?
Yeah.
We just proved that k squared has to be even, so k has to be even, right? But let's look at two things we just wrote here. Q is even. What else have we wrote up? We wrote up here. Q is even, and so is P. But what did we say P over Q was? P is even. We just proved this, and Q is even, right? So are they lowest terms?
No.
No. So what did we now? What was our original assumption? We assumed it's rational, so therefore it has to have a set of lowest terms that it can be written in. Can it? So basically, have we proven? Does it have a set of lowest terms?
No.
No. So we have run into a contradiction. Why? This is really important. You say it out. P and Q cannot both be even. If they were, then what? P over Q would equal, and we came up with new letters. P over Q would equal, or K over, no. P was equal to 2K, yeah. K over L, right? And we have a lower one. Contradiction, P over cannot both be even. If they were, then P over Q would be K over, which would be a more reduced form of P over Q. So we just came up with a contradiction. So what did we contradict? So root 2 is, sorry, and I can't write is not rational. If a number is not rational, it must be, a real number must be, therefore root 2 is irrational. Real numbers are either rational or irrational. If you prove something is not rational, it must be irrational. Yeah. Is that pretty cool?
Yes.
I think that's pretty cool. This right here, this is from the field of number theory. You can take whole classes on this in college. It's really fun stuff. I think it's great fun stuff.